What does the decimeter say?
3.6 Roentgen, but that's as high as the meter.
3.6. Not great, not terrible.
Hello everyone and welcome to another video on our own devices. I'm Jean Messier and today we're having a look at a radiation detection instrument with a fascinating local connection. This is a CAE Model 1002 Gammascint. This was manufactured in the 1950s by Canadian Aviation Electronics Ltd. Right here in Winnipeg, Manitoba, my hometown. Now, most of the radiation instruments we've previously looked at on this channel have been ion chamber detectors. And the detection element of these consists of a sealed chamber full of low or ambient pressure gas with two electrodes across which a high voltage is applied. And so when ionizing radiation passes through the chamber, it ionizes the gas and reduces its resistance, allowing a current to flow through the chamber. And this current is measured by the instrument's electronics. Now, the system isn't able to detect individual ionization events. It can only give you an averaged figure for radiation intensity. To detect individual particles, you need a far more famous instrument, a Geiger counter, which is based on a Geiger-Muller tube. Now, we're going to look at Geiger counters in more detail in a later video, but simply put, a Geiger-Muller tube is filled with low-pressure gas and has two concentric electrodes, typically a cylindrical cathode and a wire anode running through the middle, and these are operated at much higher voltages, which means that when an ionizing particle passes through the tube, it unleashes what's known as a Townsend avalanche, which is a chain reaction of electron multiplication. This allows a single ionization event to produce a very powerful electric pulse that can easily be detected by the instrument's electronics. And it is these individual pulses that make up the distinctive crackling that we associate with Geiger counters. However, both ion chamber and Geiger-Muller detectors are limited in their sensitivity and also cannot measure the energy of individual radioactive particles. To do that, you need a different type of instrument called a scintillation counter. But before we get into that, first a word from this video's sponsor, RadiaCode. Now, long-term viewers will know that I am very selective about the brands that I work with on this channel. For me to endorse a product, it has to A, be something that I would actually use, and B, fit the overall theme of the channel. And today's sponsor, RadiaCode, fits both those criteria to a T. So the RadiaCode 103 gamma spectrometer, monitor, and dosimeter is basically a modernized version of this 1950s Gammascint. Though as you can see, it is considerably smaller and also has a bunch of really neat and useful analytical features. So let's have a closer look at this and let me show you how it works. Right, so this was shipped to me in this nice heavy cardboard box with a foam lining, and this comes with the monitor itself, a USB charging and data transfer cable, and this little keychain, which is made up to look like a 1 microcurie cesium-137 check source, though this actually doesn't contain any radioactive material. And I love this little note here on the front that reads, "Don't drop and run, it's just for fun," cheeky reference to the drop and run markings on cobalt-60 and other highly radioactive sources. RadiaCode also sent me this protective silicone sleeve and carabiner, but this doesn't come with the standard kit and has to be purchased separately. So the RadiaCode 103 itself is very elegantly designed. We have the sensor at the front along with a set of indicator lights. Beside this is our display screen, a rocking selector switch, a round confirmation button, and a USB charging and data transfer port at the back. To turn on the unit, just hold down the confirmation button for a few seconds, and immediately it starts displaying the background radiation level as well as the margin for error, as well as an audio signal just like a classic Geiger counter. And just to show you this in action, I'm going to hold this up to a piece of uranium glass, which I've covered in a previous video, link in the description, and you can see the radiation jump from about 3 counts per second background up to 12 counts per second. Now, if I toggle through the selector switch, I can get my dose rate in microsieverts per hour, my total accumulated dose in microsieverts, and the energy spectrum of the radiation being detected, which can help you determine the radioisotope that you are dealing with. All of this data can be continuously recorded, with the RadiaCode 103 containing enough internal memory to record up to 1,000 hours of data, though the average battery life on a full charge is around 300 hours. You can even link this data to geographic location data via GPS using a smartphone. Now, for radiation safety monitoring, you can set up to 2 thresholds each for count rate, dose rate, and total dose. And when any of those thresholds are exceeded, it will sound an alarm: audio, lights, and vibration. The RadiaCode 103 can detect X-ray and gamma radiation at energies up to 3 megaelectron volts, dose rates up to 1,000 microsieverts per hour, and accumulated doses up to 10 sieverts. So overall, a very slick and capable little unit with all sorts of potential applications: workplace health and safety monitoring, identifying radioisotopes in a lab, or geological survey work. And indeed, the other week, I took this out hiking on the Canadian Shield in eastern Manitoba, which is a huge mass of granite full of uranium and other radioisotopes. And I was able to see the background radiation rise from around 3 counts per second here in Winnipeg to around 12 counts per second. And if you think this is as cool as I do, please follow the link in the description and on the screen below to get your own RadiaCode 103. Thank you so much to RadiaCode for sponsoring this video, and back to the topic of scintillation counters. Now, while ion chamber and Geiger-Muller detectors work on the principle of ionizing radiation reducing the resistance of a gas, scintillation counters contain a material called a scintillator, which scintillates, that is, produces light, when struck by ionizing radiation. And the first scintillation counter was the Spinthariscope, like this one, which you've already looked at in a previous video, link in the description. This was invented in 1907 by the British physicist and chemist Sir William Crookes, and contains a screen made of zinc sulfide which fluoresces when struck by ionizing radiation, typically alpha particles. And while these instruments were used to make a number of key scientific discoveries, including Sir Ernest Rutherford's 1911 discovery of the atomic nucleus, they are very limited in that the flashes of light are very faint and had to be counted by eye. Now, fast forward to the 1940s and enter a Scottish physicist named Samuel Curran, who moved to the University of California, Berkeley in 1944 to work on the Manhattan Project. Now, at the time, physicists at UC Berkeley were trying to come up with a way to measure the radiation given off by very small samples of uranium and plutonium, something that ordinary ion chambers and Geiger-Muller detectors couldn't do. Now, initially, they used a scintillator crystal made of sodium iodide, which they observed by eye, but Samuel Curran came up with the idea of combining this with a new innovation recently released by the Radio Corporation of America, RCA, called the Photomultiplier Tube. So a photomultiplier tube consists of an evacuated glass tube, one end of which has been coated in a thin layer of metal to form a photocathode, which is of course negatively charged. Behind this is a ring-shaped focusing anode, and then multiple cascades of special anodes known as dinodes, each more positively charged than the one before. So when a photon strikes the photocathode, it releases electrons via the photoelectric effect. These electrons are then directed by the focusing anode onto the first dynode, where it unleashes a further cascade of electrons via secondary emission. These electrons then bounce onto the next dynode, where they release even more electrons, and so on and so forth. This electron multiplication effect allows even a very faint light signature consisting of only a handful of photons be converted into a powerful electric pulse that can easily be detected and measured by electronic instruments. And not only are scintillation counters over 100 times more sensitive than ion chamber and Geiger-Muller detectors, but since the intensity of the scintillation, and thus the intensity of the electric pulse produced by the photomultiplier tube, are proportional to the energy of the ionizing radiation that produced them, scintillation counters are able to measure the energy of individual particles. Now, today, scintillation counters are widely used in multiple industries, including medicine, the nuclear industry, geology, workplace health and safety, and things like that. And a number of different materials are used as scintillators. The most common of these is thallium-doped sodium iodide, and this is mainly used to detect gamma radiation. This not only has a very broad detection spectrum, but also a high quantum efficiency. That is, the efficiency with which the energy in the original ionizing radiation is converted into light energy. Other scintillation compounds in this class include thallium-doped cesium iodide, bismuth germanate, and cerium-doped lutetium iodide. Now, zinc sulfide, previously used in spinthariscopes, is still widely used in scintillation counters for detecting alpha particles, while lithium iodide is used for detecting neutrons. There are also a wide variety of organic compounds used as scintillators, including anthracene and substances whose names I'm not going to attempt to read out here, but go by the abbreviations PPO, POPOP, PBD, and BPBD. Some of these, like anthracene, can be used on their own, but typically they are mixed into a plastic matrix, which can then be molded into any convenient shape. In this form, the active scintillator materials are known as fluors. Organic scintillators can also be dissolved in organic solvents like toluene, benzene, and xylene for use in liquid scintillation counting. This involves mixing the material whose radiation emission is to be measured into the scintillator liquid itself, achieving high detection efficiency via intimate contact between the radioisotope and the scintillator. Finally, there are also glass scintillators made of cerium-doped lithium and boron silicates, which are particularly good at detecting low-energy or thermal neutrons, such as those produced in a nuclear reactor, as well as gaseous scintillators composed of mixtures of nitrogen and noble gases like helium and argon. And of course, today, most scintillation counters have replaced the old photomultiplier tube with charge-coupled devices, photodiodes, and other more sensitive and less power-intensive sensors, allowing the instruments to be radically miniaturized. Now, this finally brings us to this particular unit, the CAE Model 1002 Gammascint. Now, while the scintillation counter itself was invented by Samuel Curran at UC Berkeley in 1944, the practical portable scintillation counter for industrial use has its origins right here in my hometown of Winnipeg, something I was not aware of until I started research for this video. So the story of this instrument begins in 1948 with one Dr. Robert Pringle, another Scottish physicist who, during the war, worked at the University of Edinburgh with the famous German physicist Max Born. And through this work, he became aware of some of the technological advances made by the Manhattan Project, including the development of the scintillation counter. Now, in 1948, Pringle moved to Winnipeg, Manitoba, where he became a member of the physics faculty of the University of Manitoba. And in January 1949, he was approached by the head of the geology department, George Brownell, who asked him if it was possible to produce a radiation detector 100 times more sensitive than a regular Geiger counter, which could then be used to prospect for uranium ore. And Pringle said, yes, there's this neat technology we developed during the Manhattan Project. And together with his graduate student, he quickly put together a prototype. And in the summer of 1949, they took this prototype to Lake Athabasca in northern Saskatchewan and Alberta. And this expedition was so successful that the following year, Pringle and Brownell contracted the local Winnipeg firm Halross Instruments Corporation to produce the world's first commercial scintillation counter, the Model 939. This was housed in an aluminum alloy case with a provided carrying bag and shoulder strap, and had a removable detector probe with a sodium iodide scintillator crystal, which could be stored in an internal compartment. And this sold for $820, a whopping $10,700 today, and could measure up to 6,000 counts per second. It was advertised as being rugged enough for field prospecting work and capable of distinguishing between uranium and thorium ore. Now, for several years, Pringle and Brownell effectively had the scintillator market to themselves, and in 1951, they formed their own company, Nuclear Enterprises Ltd, to manufacture the instruments. However, by 1955, several American companies had started producing scintillators that were a lot cheaper than anything that could be manufactured in Winnipeg. So the decision was made to move Nuclear Enterprises to Edinburgh. And there, the company was so successful that apparently Pringle was forced to flee to Monaco to avoid high UK taxes. Now, meanwhile, Halross Instruments, although they were the first to produce a commercial scintillation counter, had a product line mainly consisting of agricultural instruments, including grain moisture testers like the one we had a look at in a previous mystery object video. And they ended up going bankrupt in 1955, whereupon they were purchased by and became the Western division of Canadian Aviation Electronics Ltd of Saint Laurent, Quebec. And CAE Ltd is a fascinating company in its own right, but their full story is a bit beyond the scope of this video. But very briefly, they were founded in 1947 by ex-Royal Canadian Air Force officer Ken Patrick, and specialized in repairing and installing radios, radars, magnetic anomaly detection or MAD systems, air defense computers, radiation detectors, and other electronic equipment for the RCAF. In 1952, however, they were contracted to develop a flight simulator for the Avro Canada CF-100 Canuck all-weather interceptor, and this quickly became the company's bread and butter. And today, CAE Ltd produces a number of different products, including flight simulators, simulators for the medical field, and control and monitoring systems for nuclear reactors, oil and gas pipelines, and other industrial fields. Now, starting in 1955, the Western Division of CAE, located at 387 Sutherland Avenue here in Winnipeg, produced a wide variety of radiation detection equipment. In addition to the original Model 939, there was also the Model 963 scintillometer, which looked very much like this unit but was more sensitive, able to measure between 300 and 30,000 counts per second and 0.025 to 2.5 milliröntgen per hour using a sodium iodide scintillator crystal. It weighed 3 kilograms with batteries and sold for $695, or around $8,200 today. There was also the cheaper Scintillo counter Model 911, which sold for $495, $5,800 today. The transistorized Model 1001 Transient and Conqueror, the latter of which weighed only 1.7 kilograms, and the Pattern 58, which was a regular Geiger-Muller counter in pistol form. And finally, there was the Model 1002 Gammascint, which apparently was the economy model of the product line, but I haven't been able to find any information on how much this originally retailed for. So as you can see, this is designed rather like a binoculars case with a shoulder strap and a curved casing that would fit nicely against your body, perfect for geological fieldwork. And you can really tell that this was designed in the 1950s. This blue-green speckled surface here is very mid-century modern. Now on the end here, we have a little red dot, which indicates the location of the detection element. If we look at the top, we have our data plate, which shows that this was produced by the Canadian Aviation Electronics Ltd. Western branch of Winnipeg, Canada. We have 2 jacks here for headphones. We have a selector switch with 3 positions, off, 1 times, and 10 times scaling. If we look at the readout gauge, we can see that this can detect up to 1 milliröntgen per hour. So that's pretty much it for the exterior of the unit. Let's actually open this up and see what the interior looks like. And we do that by simply removing these 4 screws around the top rim. All right, and then the interior chassis simply lifts out. And there's really nothing much more to say about the casing. This is made out of fiberglass, which is transparent to gamma rays. And yeah, there's really nothing in here except for the mounting points for the shoulder strap. So I'm going to set that aside. Right, so on the inside, we have our electronics, and this consists of 2 different modules. We have an amplifier up here in the front with 2 vacuum tubes, and this would amplify the output of the scintillation crystal and photomultiplier tube and integrate it to produce an average dose rate in milliröntgens per hour. And in the back here, we have a transformer and 2 more vacuum tubes that form an inverter to convert the low voltage of the batteries into the 1200 volts needed to run the photomultiplier tube. And then at the back here, we have a potentiometer, which is used to calibrate the unit whenever the vacuum tubes are replaced. Now, in the bottom, we have our battery compartment with 2 battery connectors, and presumably this would have used standard radio batteries like these here. And these are actually out of a really cool home-built Geiger counter that I'm going to be covering in a future video. However, I've not been able to find a lot of detailed information on these units, much less manuals, though on the other side here, it says 67.5 volts, which is the standard voltage for a B radio battery, which would have supplied the B voltage for the vacuum tubes and would also have been stepped up by the inverter to run the photomultiplier tube. And the other one was probably a 1.5 volt battery to run the filament heater on the vacuum tubes. Though if any of you watching have actually used one of these units and know exactly what type of batteries this would have used, please let me know in the comments. Now, finally, we get to the detection element itself, which is housed in this canister, and this is made out of something called mu metal, which is an alloy of nickel, iron, copper, and chromium, which is used to protect sensitive electronic components from magnetic interference. And I can remove this canister by undoing these 2 screws in the bottom, and that comes out just like that. And then you remove the 4 screws in the top, and the whole package comes out. And here you can see the sodium iodide scintillator crystal strapped to the side of the photomultiplier tube. And this appears to have been repaired at some point because the 2 are held together with a couple of lengths of electrical tape. And on the inside of the shielding canister, you can see a little foam pad to protect the end of the photomultiplier tube. And that's basically all there is to the Model 1002 Gammascint. Now, probably the main reason that it's very difficult to find specific information on these units is that they weren't manufactured for all that long. See, in the late 1950s, CAE Ltd. decided to move away from consumer products and focus mainly on large government and industrial contracts. So by the 1960s, their consumer products, like their radiation detectors, had all but disappeared from the market. Now, as I said before, scintillation counters are still widely used in a wide variety of industries. And before I end the video, I will leave you with a very funny story told to me by my father, who actually used to work as an exploration geologist in the Canadian North, prospecting for uranium. Now, one day in the 1970s, he was at the airport headed back to the north, and he was carrying a scintillation counter, a very different unit from this one that looked like a big gun. It had the detection crystal in the front, the readout gauge in the back, a pistol grip, and then the batteries in a hip bag. And this came in a fitted case filled with foam. And he looked at this and realized it looked like something out of James Bond. You had the gun itself and a couple of batteries that looked like magazines. And so he decided to play a little joke, and he put the case in the X-ray scanner for carry-on luggage. And he watched as the board security guard watching the feed very quickly sat upright, and his eyes bulged out as he saw what looked like a gun with a couple of magazines in the X-ray. So my dad starts chuckling to himself, but immediately he feels something behind him, turns around, and there are two RCMP officers standing right behind him, and they ask him to go into the back room with them. But thankfully, he's able to show that it's not a weapon, it's just a radiation detector, and they let him go on his way. It truly was a different time. Anyway, that's all I have for you today. Thank you so much for watching, and thank you to RadiaCode for sponsoring this video and sending me an example of their product for me to play around with. I'll see you next time in another video, or look at yet more radiation detection equipment and other fascinating devices just like this one. Until then, I'm Jean Messier from Our Own Devices. Have a great day.